Continued fractions. This is what a continued fraction looks like, where a and b can be any real or complex numbers. A simple continued fraction has all its denominators being 1, and a has to be an integer. This finite simple continued fraction can be represented in many forms. In this method, the lower plus signifies the step-down process at each stage. Or we can just write down the partial quotients, which in this case are the a's. Any rational fraction can be written as a unique finite simple continued fraction. We first separate the integer and leave the smallest positive remainder. Next, we replace the remainder with 1 over its reciprocal, and we repeat until the remainder is 0. Here is an example. I will now show you a quicker method that will directly give you the partial quotients. As you can see, it is very similar to long division. However, we're using the remainder of each stage to divide the previous divisor. First, we're using 9 to divide 29, and then 2 to divide 9, and then 1 to divide 2 until the remainder is 0.
Since a rational number cannot be expressed as a fraction of two integers, they can only be expressed as infinite simple continued fractions. We will be expanding quadratic irrationals, which have the form I plus or minus root j over k, where I, j, and k are integers. The method is still the same. According to Lagrange's theorem, any quadratic irrational has a continued fraction expansion that is periodic from some point onwards. For example, here. Here is an example. In order to expand root 2, we first separate the partial quotient and the largest positive remainder. Next, we flip over and we try to simplify it. Eventually, we can see that we have to expand root 2 minus 1 again. We can see that this is an indefinite cycle. Therefore, all the remaining partial quotients will be 2.
We can cut off continued fractions at various stages, which will give us the convergent at that stage. For this expansion, the first convergent is just 3, the second is 3 plus a third, and so on. We're just ignoring everything after the plus sign at each stage. So if the continued fraction is finite, the last convergent will be the continued fraction itself. There is also a recurrence relation between the numerators and denominators for each convergent. This is listed here. We define the negative first and zeroth p and q to be 0, 1 and 1, 0 respectively. The best way to calculate convergence is to use a table. On the first column we have I, the partial quotients, nominators, denominators, and convergents. A and C don't have any values for minus 1 and 0. Then we put down the defined values for P and Q and the partial quotients. From the previous equations, we can see that to get the current nominator, we need to multiply the previous nominator with the current partial quotient and then plus the nominator before that. In this case, it would be 1 times 2 plus 0. Next, it would be 2 times 3 plus 1, and so on. We do the same thing with denominators to find the current denominator. First, it would be 0 times 2 plus 1, and so on. Finally, we combine P and Q to find the convergence. See how the last convergent is 67 over 29, which is the same as the original fraction. When solving simultaneous equations that are consistent, we will end up with a linear equation with an infinite number of solutions. But this isn't very helpful when dealing with discrete objects, where we only want integer solutions. We will be solving linear Diophantine equations using continued fractions. They have the form ax minus by equals c. For there to be integer solutions, a and b must be co-prime integers. A very useful property of convergence is that pi times qi minus 1 minus pi minus 1 times qi is always equal to minus 1 to the power of I. We can rearrange finite simple continued fractions in order to obtain the desired difference of the final convergence. 9 originally has 4 partial quotients. However, by splitting 2 into 1 plus 1 over 1, we get 5 partial quotients. And now the difference of convergence would be minus 1 rather than 1. In this question, we can see that 37h plus 22c is equal to 2370. And we know that c and h must be integers. But how do we solve it? We first need to know how to solve ax minus by equals 1. Since a and b must be coprime, the final convergent of a continued fraction a over b must be itself. Using the difference of convergence, we get the following equations. We need the number of partial quotients n to be even. If n is odd, rearrange the continued fraction. Either way, we end up with this equation and the particular solutions, x0, y0. Next, we subtract it from the original equation, and since a and b are coprime, b must divide x minus x0, so we can express it as tb, where t is some integer. Now we have the general solution for x. By subbing tb back, we can find the general solution for y as well. Let's try solving 67x minus 29y equals 1. We already know that 67 over 29 has the partial quotients 2, 3, 4, and 2, and we've already calculated all its convergence as well. So according to the difference of convergence, we know that 67 times 13 minus 30 times 29 equals 1. So the particular solutions are 13 and 30. Now we subtract it from the original equation, and we end up with this. 67 and 29 are coprime, and x minus 13 must be an integer. So if we divide both sides by 67, y minus 13 must be a multiple of 67 for the right-hand side to be an integer. Therefore, we can express y minus 30 as 67t, where t is some integer, and we have the general solution for y. By subbing 67t back, we can find the general solution for x as well. We can now solve ax minus by equals c. We first find the pair of particular solutions to ax minus by equals 1. Next, we sub it in and multiply both sides by c. After subtracting it from the original equation, we can now find the general solutions. Thank you for watching. If you're interested, there are many more applications of continued fractions, such as approximating numbers and solving logarithms.